We are in the second course of our school. The course will be delivered by João Marcos and Walter Carnielli. They will present also 5 classes. The first 3, João Marcos will be giving the classes, and Walter Carnielli, the last 2 ones. Okay, João Marcos, we are happy to receive you because João Marcos was our student here. He is associate professor at the Department of Informatics and Applied Mathematics of the Federal University of Rio Grande do Norte in Brazil, and collaborates with the Security and Quantum Information Group, IT, in Portugal. His work focuses on non-classical logics, especially logics of formal inconsistency. João Marcos took his PhD here at Unicamp, at CLE, under our colleague Walter Carnielli, in a joint doctorate with Portugal. Walter Carnielli is full professor of logic at the University of Campinas at Unicamp, and served as director of CLE for several years, serving as well as editor and member of editorial boards of major journals. With relevant contributions on both technical results and philosophical aspects of logic, Carnielli is one of the pioneers of the Brazilian School of Paraconsistent Logic. He was also president of the Brazilian Society of Logic for 2 terms and founded the ANPOF Logic Work Group. Carnielli published several books in the field of computability, logic, and philosophy of logic, as well as books for the general public. Grantee of the Alexander von Humboldt Foundation, Carnielli received national and international awards, such as the Telesio Galilei Academy of Sciences Gold Medal for 2013, and 3rd place in the 2007 Prêmio Jabuti in Exact Sciences, Technology, and Information. In 2019, he received the Capes Prize for the best PhD thesis in philosophy together with his student, Bruno Mendonça. Carnielli has interests in the area of artificial intelligence and rationality, and is currently vice president of the Advanced Institute for Artificial Intelligence and president of the Scientific Council of the Model Institute in Brasilia. Okay, João Marcos, okay, you have the word. Thank you.
Thank you very much, Vitor. Thanks everybody for coming. Thanks for the invitation. Very happy to be here indeed. It's been a long time since last time I had a chance. The course, as you can see, is going to be on non-classical negations and classical recapture. I'm going to explain what that means. So the talk today is going to give you a first view of the scenario where things are going to happen later on. And I just wanted to correct a little bit that I'm currently a full professor at the university in Natal, which is somewhere around here. But if you want to meet me from the middle of the year on, I'm moving to the Department of Philosophy of Santa Catarina, Florianópolis. So it's going to be further here, as you can see. As north is ours, south is our north. Okay. Now this is a historic photo that I found. That's the only piece of history in my talk. In September of 2000, the first ever talk called A Taxonomy of Systems happened in the University of São Paulo, and this was 23 years ago. I'm about 23 years younger than Walter, so I'm his age now. And Walter is about 23 years younger than Newton, the Costa. So it's up to you now to be around 25 or 26 and continue this tradition here. Now, the talk is going to be organized today. The session is going to be organized into 6 parts of different lengths. The first one is going to introduce the notion of consequence through different lenses. So this is not going to be your expected or typical talk on logic or on power consistent logics, but bear with me that I hope it will make sense at the end. Okay, the players in the first part is going to be things like sentences and what I call consecutions. Some people call sequence, but I prefer to call them consecutions because they belong to consequence, a way of organizing the sentences so that you can pass judgments on them. And I'm going to introduce something that I call a compatibility relation and its complement, which is known as the consequence relation. And talk about logical principles very little, but enough for you to see that there are pure versions of these principles that can be stated without any reference to negation at all, and how to characterize logical constants, not just negation. And I will assume that the logics I'll be talking about here are formal, and the way that we sometimes guarantee that by ensuring something that's called substitution invariance. And explain what that means. So the first slide, as I said, atomic sentences. Let's suppose that this is a whole proposition for the moment. It doesn't really matter much. And with the help of these atoms, you might build sentences through some algebraic trick, recursive trick. And the consecutions at the moment are just going to be pairs of sets of formulas, of sentences, sorry. Now, the properties that I want you to consider at the moment for what I would call a judgment compatibility relation. Apologies, I'll close it. The first one I will read, then I'm going to write the first one, what I'm reading. But the first one said that whenever you have something that I call a satisfaction statement, I'm going to explain what that means. A fragment of it's still a satisfaction statement. And the other two say that you are to disallow judgment gluts and judgment gaps. Now, I'm not saying that you must subscribe to these principles, but I'm saying that if you do, we define a certain kind of relation on sets of formulas, binary relation, which I call compatibility relation. And I'm going to explain how to read this sort of satisfaction statements in a minute. I also want to say that if you want to interrupt, ask for clarification, at the end of each part that's counting here, it would be the best moment, but please feel free to interrupt before, because this first part is like 38 clicks, so you might want not to wait to the last one. Okay, now, what do I mean by compatible? Let me assume that we have judgments available to us, and rather than having just the assertion judgment, which is very common, I'm going to introduce also denial judgment as primitive. This is very common in the bilateralist approach to logic, and as you will see, it's quite appropriate to what we're doing here, which is why it's symmetrical environment for doing logic. Okay, so the way I'm going to read satisfaction statement like that is saying that the sentences on the left-hand side are asserted, while the ones on the right-hand side are denied, all of them, simultaneously. So in a certain sense, I'm saying that it's compatible to do or to establish all these judgments at once, to assert everything on the left and deny everything on the right. Okay, with that reading, going back to those formal stuff that I did before, you could read the first one as saying that if the sentences on the left may all be asserted while all these are denied, so in particular, you might assert part of the ones which are on the left and part of the ones which are on the right. Now, the second one says that you might not know this. This is saying that there is an empty intersection. They exclude each other. Right? They're disjoint. I like this notation for disjointness. This is saying that if this satisfaction statement can be held, then this means that there's nothing in common in between what's on the left and what's on the right, meaning that you cannot assert and deny at the same time. Produce class. And the third one says that whenever you get a set of formulas, you have to choose where to put them. Part of them are going to go to the asserted side, and part of them are going to go to the denied side. I might not agree with this, I might not want this, but that's how the definition is set at the moment, how the relation is defined at the moment. And I think there are some interesting consequences of this definition, in particular that you can formulate the principle of non-contradiction, the principle of logics will deal in a very pure way without negation. If you just take, if you just consider phi and sigma to be singletons containing this sentence phi, so you say if you put phi and phi here, then the two sets are going to be disjoint. They cannot be disjoint, so you cannot put phi on both sides. So you cannot assert and deny a formula at once. And here, if you take delta to be a singleton and you try to break it into two parts, you're going to see that this formula has to go to one side or the other, so you must either assert or deny. Okay, so it's a pure versions of these logical principles. Some people like to write these principles using negation, conjunction, disjunction, and so on, but we don't need to. We might have other versions of the principles later on. Okay, so very abstract, but finally a little bit useful already. This is what we had before, and I'm going to transform this into the complement. So I'm going to pick up another relation, which is the open triangle over there, which is going to be the complement of the black triangle. And then I'm going to rewrite stuff. The first one we rewrite using contraposition. You have something that people sometimes call monotonicity. The second one, overlap or reflexivity, basically something called single conclusion logic, which I'm also going to over. And the third one is a form of cut. So this is the form in which most people have been introduced to the notion of consequence in logic, if they have ever gone into a bilateral notion of consequence. I'm going to get to the unilateral one in a moment, but this is the form in which you'll find in the books. And if it's the complement of compatibility, I might call it incompatibility, judgment incompatibility. That's what we're manipulating there. I think it's useful to know how to read stuff. So that's what I'm doing here. And as you see, this symbol here says that there is something in common. There is something in common in between what's on the left and on the right. So what's on the right follows from what's on the left. There is an only intersection. Just to test our reading, just take your favorite classic implication. You might not your favorite implication, your favorite classic implication. And it might be characterized easily, as I'm going to show in a later slide, by three axioms involving pairs of sets of formulas. But I'm just taking out the braces here so that we can more easily read this. The first one says, at the moment, that it's not compatible to assert this implication while you're asserting the antecedent and denying the consequent. Hope it does make sense, or else you don't like modus ponens. You might not. But the classical implication likes it. And this other one says that it's not compatible to deny this implication while asserting the consequence, or the consequent of it. And the third one says that it's not compatible to deny the implication without asserting the antecedent of the implication. And if I write these three together, just give you classical implication in a certain sense. I'm going to explain what's the sense in which it does in a moment. For the moment, I'm doing abstract logic, so let's go back to consequence, and let's keep writing things in terms of the consequent relation symbol rather than compatibility relation, which is the one that I like the most. And let me just transform it into the single conclusion version, in which you have a single formula on the right. Yes, please.
Earlier you had an empty triangle without anything on the left.
Yes.
What does that mean?
That it's not compatible to assert everything that's on the left. They're jointly incompatible. You can't have them all. Okay, so let's write it down. Five. So how do I read this?
Left. Right.
So if and only if this is not the case. I read it. So this says that it is compatible to assert all this and deny all this. You may do it. This is saying that you may not. Like in that example, you may not. If here is 2, you may not assert all this while denying this, or you may not assert this also the antecedent while denying the consequence. Okay, now take out the denying part. Just say the asserting part. If I write something like this, I'm saying that you may not at once assert all the formulas in there. But if you don't like it, you just put an empty set here. Right? So you may not assert all formulas in there while denying all formulas in here. Then you have your denial back.
And same the other way around.
Yeah, same all the way around. So this, in general, will be written without the empty set. It's going to say that you may not deny all the things here at once. So later on, you're going to see things like here. Saying that you may not deny both at once. Intuitionistic logician defers. But he says, yes, you may. Okay? Now, at the moment, I'm not going to introduce negation, but this is going to appear later on. Is that all right? Is that makes sense, everybody? Okay, so yes.
I didn't quite get why wouldn't you deny phi and phi implies? Okay, no, never mind.
If you prefer, later on you can just read this as true and false, right? If this is false, it's going to be true. Okay, the intuitionistic logician doesn't like that.
Yeah.
The logician is fine with the commas on this right side, right? Okay, thanks for the questions. Thank you very much. It helps. Shouldn't assume everything I'm saying is perfectly understood, especially because some of them are quite different from this, which is what most people have seen when they have seen consequence relations. Call them unilateral consequence relations. There is directionality. You think of left containing your premises and right containing your conclusion. The conclusion. It's quite weird actually, because in general we have several conclusions. But I don't want to collect them conjunctively. In a sense, we're collecting them disjunctively. I'm saying that when you put things on the right, you have a set of alternatives. One of them, as I'm going to show you an example, has to be the case. Just wait for some examples if you think this is going to eliminate. I'm going to give examples of proof systems and semantics involving this. Now, these definitions, this is very common, as I said, and you can recover a single conclusion version of logic from a multiple conclusion one in a very simple way. That's the simplest minded way of doing that. Is just that, well, we'll say this can have a set of formulas on the right. What if it's a singleton? Right, it's a singleton, so it's single conclusion. But also you can do it at the other direction. You can put a singleton on this side, and still you have something which has the properties of consequence relation. Most people don't think of that side because they're not used to put sets of formulas on the right. It's the same. It's going to have all these properties here. You can think of the first one as being an assertion-based notion of consequence, saying that if you assert all this, then you must assert all that. Then you have your implication back. If you want your implication, we're missing your implication. Meta implication. I was reading things as conjunctions, right? All negations of it. And this is saying that if you deny all this, then you must deny that. According to this approach, as denial doesn't have to be the complement of assertion in principle, this might be totally different ways of looking at logic. Okay, so the other way around is hard because when you have something like this, a T-consequence relation, you might have several different counterparts as consequence relation, so set framework. So we won't even try to do it, but you might have several ones. I'm just pointing out that obviously I was working on the more general stuff and it's easier to take particular cases. But you cannot recover all the phenomena that we had before when I talked about the set approach, the as consequence approach, which is the natural one. It's the one that I'm going to use until the end, at least the first 3 sessions. So get used to it. I'm going to need it. Ask questions if you need. It's a course. Okay. What about doing logic in this environment, having pairs of sets of formulas? Well, one might think that if you're doing presenting an axiomatic system that you might have not just axioms, but what we call anti-axioms. You put things on the other side. So rather than saying that, please assume that this formula A is the case, is my axiom, you say, well, please assume that this is the case, and put your empty set here if you prefer. Okay, because here you're saying that you must assert A or you cannot deny A. And here you're saying that you must deny B, you cannot assert B. Okay, so this is interesting to have a look at because there are many other ways in which you can induce something called a consequence operator using a symmetrical approach to consequence. For instance, you might assume that you have some set of things which are the background denied sentences. If you forget this sigma, if it's empty, then you're going to read here that phi follows from gamma 1. That's what you were used to. But what if I add this sigma here? I'm adding a set of background things from my theory, which are the sentences you're supposed to deny. And on the other side, if I have an empty phi here, so I'm not adding any asserted sentences, but if I do have a set of asserted sentences, A of phi, if I assert all the sentences in phi, then I want to take them into consideration as premises in establishing what follows from what. Now, what's interesting is that for every choice of sigma, every choice of phi, you have a different single conclusion consequence relation associated to the same multiple conclusion one set consequence relation. So there is actually a beautiful structure behind all this, and you can study the bilattice of consequence relations that can be induced by this. And you can recover what I said before. For instance, if you have an empty set of denied sentences, so saying that something is a consequence of a set pi is saying that it follows from pi according to the assertion-based reading. So if you assert all the things in pi, then you must assert phi. So you can recover what I just presented in the previous slide. And you can also recover the denial-based notion of consequence just by taking an empty set of asserted background, asserted sentences. So I presented just a particular case on the previous slide, and here I show there are so many other things which are maybe associated to this approach. Now, you might ask, where is this operator you talked about? This operator on pairs of theories. There's a very simple way of defining it, which is defining it as receiving a pair of theories and giving you back the pair of theories. Which one's that? Those that contains the consequences. And to produce the consequences, you use these two things you have in here. You take the sigma as a set of denied background assertions to produce the consequences of pi, and vice versa with pi and sigma. Now, what is this? What kind of properties this operator has? I'm going to show you. Let me just remind you that everybody knows the properties of closure operator, Tarskian closure operator, which is one-dimensional. So it receives a theory and produces the closure of it. It generalizes the notion of closure in topology, the Kuratowski axioms, throwing away two of the axioms. And I won't even read them, but you can easily imagine that they're still talking about monotonicity, reflexivity, and cut. Now, how do they look like in the two-dimensional approach? Like this. This obviously still looks like monotonicity, and it still looks like extension, like the reflexivity, and it still looks like that, like the fourth did. But there is a fourth one. Something we found out later on. This, if you don't add this, you don't have an axiomatization of what we want to capture. And what it says is basically that if you're looking for the closure of this pair of sets, you have to assume that it contains the intersection of all the consequences of the maximal theories. A bit complicated to use in practice, but you actually need it to generalize. And there is no counterpart for this in the one-dimensional approach. So it's a discovery to find out that you can actually do it. So it seems perfectly respectable at the moment to have this notion of closure and consequence extended to the two-dimensional approach, motivated from the incompatibility reading. I just wanted to say that actually we could even simplify this. You can say that actually logic is about the truth and the falsity. And what that means is that you can give to any logic, to any consequence relation obeying the axioms that are presented before, bivalent semantics. And it's very simple. And this particularly applies when you have homomorphisms here in between the set of sentences and the set of, and the matrix, the set of truth values that you have. But this H doesn't need to be homomorphisms. It doesn't matter. The idea is very simple, is that whenever you have your favorite semantics and you take your sentences to designated value, which I call the set of assertions here, when you assert the sentences, then you're going to instead take the asserted sentences to the truth and take the denied sentences to the false. So it might not be useful, but it works. And the notion of consequence that's induced by the new collection of valuations, which is the one produced by this composition, is the same that you had before. So you might say every logic has semantics using bivaluations. So it's a very general result, not necessarily useful. In some cases, you can produce some algorithms for this reduction, and then it becomes pretty useful. Particularly when it gives you some decidability procedure, which is based on just two values, two signs, or two labels, or whatever. Now, you might be missing your values. We have so many values and so many possibilities before in general, and all of you have heard about many value logics. There'll be a course on Lucas-Shevich logic here. And you can't recover them if you stay on this state. But you could if you were to allow the principle of non-contradiction and principle of excluding error the way I formulated them to fail. Then you would allow for things to be really gaps and glasses. And I'm going to show a picture of this later on. Just a hint that this can be done at the abstract level. Okay, where is this all heading to? I still need one more thing, which is not related to topology in principle, but it's very algebraic mind, in which I will assume, you don't need to, but I will assume that every logic is substitution invariant. And what that means is that if you can infer something from something else, introduce some substitution, you can still infer. You change your propositional variables for complex sentences, what you concluded before you can still conclude. So there are many ways to formulate it, depending on whether you have the compatibility, the S consequence, the T consequence, the T operator, the S operator, but it all amounts to the same effect. Now, what this helps me with is that I don't have to use all the quantifiers that people use when they speak and that they forget to write when they formulate things like this, saying that there is a formula, there is a sentence and another, such that it is compatible to take this disjunction to be asserted while denying this conjunction. And I'm sure all of you think this is quite natural, that the conjunction shouldn't follow from disjunction. Now, if I use this principle of substitution invariance, I can just write this without using the quantifiers, which is what I'm going to use, better to in these sections to make life easier, except for some particular sliding which I want. Now, and also this modus ponens, as you've seen before, again, that's very simple to see. As a particular case of these universal quantifiers, you could put atomic sentences, right? It's just using the elimination of the universal quantifier. Now, what about the other way around? Well, if this is the case, you perform a substitution, and then you can conclude this for any formula phi that you put in the place of P and any formula of psi that you put in the place of Q. So you don't need the quantifiers, right? You can just write things without them. Okay. Now, I hate when they are needed and they're not written. I'm explaining to you why you can't avoid in this case. But you do need substitution invariance to do that. Okay, before starting the next set of slides, if there are questions, complaints. No, it's fine. Yes, please.
Could there be, you talked about the certain commitments and denied commitments,
Yes.
and that seems like you're like fixing the side and varying the other. That seems like that's like a bit of actually there's a structure which is bilateral.
Yes.
So would you do the same thing by taking two compatible sets and then talking about their consequences?
Yes, I'm going to do that. I'm going to talk about the situation in which assertion and denials are not the complement of each other. So you can talk about being not asserted and being not denied, and this will not coincide. Is this what you implied? No.
When you talk about the theories or a set of assumptions,
Yeah.
that assumptions could be asserted or denied.
Yes.
But it seems to me you could define a single notion
Yes, that's
which
so.
makes a compatible pair. And
Yes.
one is constant.
Yes, and this is the one that we have axiomatized here with a pair, right?
It's the same.
Yes. So this closure operator, two-dimensional closure operator, corresponds to two-dimensional consequence relation, which is the complement of the incompatibility relation that I presented at the beginning. So they're all connected. Yes. Thank you. Okay, so second part, I'm just going to illustrate some things you could do with this stuff. It's not really big theory of semantics in group theory. I'm going to give you some examples of how automatically you can associate to any given semantics consequence relation, as consequence in fact, and some appropriate group theory for doing this. Awesome. So just to see what's on the slide, I will explore this by building outlook. Separation between the true and the false. And then I'm going to talk also on the proof theoretic side that you can talk symmetrically about axioms and anti-axioms. There's these kind of new consecutions that will turn into sequence that you can see, not sequence calculus. I'm going to talk this about the third lecture. Now, and I'm going to show you how that you can look at truth tables and extract from them axioms by way of what I call determinizations of the truth table. So every time you have logical matrices, non-deterministic, partially non-deterministic, whatever, things called logical matrices, automatically they will be associated to S consequence relations, also to T consequence relations. And there will be some particular kind of axiomatic processes which are also automatically associated to consequence relations, and vice versa. Every consequence relation might be recovered by some collection of logical matrices and by some proof systems of the kinds that I presented here. Okay, so let me show you an incredible story of a connective which didn't quite know what it wanted to be. It was a binary connective, fully indeterministic. And that was just the beginning. There were more days in this story, and the next day, someone says, I'm going to tell you what I want. And particularly, I want to disallow some situations. Remember, this is incompatibility, so I want to disallow the situation in which this phi is asserted. This is being true here, because you push assertions into the truth. This guy is denied, so it's in false. And at the same time, this guy is being asserted. So this is no longer an option. This is what that rule, or that axiom actually talks about. What about this one? It says that, well, you cannot assert the second guy in here, so you cannot do this, while at the same time denying the guys in here. It's incompatible. So you don't have any longer these two possibilities. Making the fully indeterministic truth table more deterministic. And I claim this is how they're all born. Now, the third thing you might want to say is that it's not compatible to deny this guy, so that's the first line here, while also denying this guy, so I throw away this and this and. And, as you know, this gives the implication we talked about, classical implication. So any truth table might be recovered like this from classical logic, and if you're not doing classical logic, you can do the trick before reducing them into binary versions and then perform some other tricks on top of that, which I'm not going to show. Okay, so you could just substitute this copyright connected. I have no copyright on it for implication. And here I'm going to show you how those things produce actually rules for quite decent calculus, which I'm not going to name until the last click, because or else you're going to see it's not decent. Okay, it's quite decent because the first three things here are the determinization of the conjunction truth table, the other three of the disjunction, and then there's a comma here, as you see. The other three we just did, implication. And this is for negation, and there's an empty thing on the right here. You got it here. Now what can we do with this? Well, prove stuff. The way we prove stuff with this kind of calculus is like this. Well, you want to prove that this is a theorem, meaning that it can be put on this side while the empty set is put on that side. The way to do it is use R9, taking Q as being P, and then this is already what you want. You continue on this side by using R8, again, taking P in place of Q. And then because in both cases you arrive to P implies P, and that's what you were looking for. Now, a more interesting example, which I don't need to go into details, you see it uses the rules that we had before, and it has three things here at the end. Let's look at the leaves. Here, it has a star. The star means that there was a problem here, and the problem is given by R10 because you have the conjunction of P and Q, and you have the negation of the conjunction of P and Q. So this is a discontinued branch. It can no longer be developed. That terminology of development is by William Neal. Okay, so actually he used that, he introduced it. Said I wouldn't go to history. There it is. Okay, and on the other side you have not Q, and here you have not P, but here I was looking for starting from this and getting one of this, right? And I do, because I disconsider this, I get not Q, which is one of the things, one of the alternatives that I was looking for, and I get not P, which is the other alternative. So I can say that I have proved this set from that set of these two formulas separated by a comma. Now I'll tell you what I'm doing. This is a Hilbert-style system. That's why I didn't say before, because all of you hate Hilbert-style systems, of course. They're so useless. They're not. If you do them this way, using set, actually it's analytic. You can implement a fully automated procedure for looking for these proofs, and the idea is that if you look here, along the development, you do not ever need to use anything which is not a subformula of the original formula. So you have a finite search space. It's very, very simple. Now you might complain that this is not what you have seen before. It's called Hilbert-style, but it does the same thing. It just generalizes. What you have seen before is the tree which had just a single branch. And this is allowing you to explore alternatives. Okay, questions? Yes?
In that system, is every proof is optimal?
No. Optimal in the sense that you're going to find the shortest one?
Yes.
Not necessarily. For that, you need some heuristics. You need a way for looking for them.
You can assert that there is one
Yes.
optimal proof?
Yes, you can assert that. Give a procedure to find an optimal proof depends on the logic that you have at hand.
Some kind of normalization.
Yes, you could do that. Yes. Yes.
Yeah, actually, to me, they look closer to Tableau and natural deduction. I mean, it's
They do, but remember that the usual tableaus, not the ones that you do, which are much better, but not cut-based tableaus, not the ones that Alejandro is doing, really great. They only analyze, they don't synthesize. So you don't have in things which are not KE tableaus or cut-based tableaus, things like this, right? Like this. You would have like just decomposition. Yeah. So tableaus can be seen sometimes as Hilbert-style, sometimes they can be seen as secant calculi. I'm not going to enter into that. I'm going to present some secant calculi which cannot be seen like this. But this is the thing that is associated to any constant relation. That's the generalization that you have. It was well known that for the single conclusion case, you could associate always Hilbert-style systems, but they're useless.
And
Now, for the set case, you can associate useful ones. Yes.
And computationally speaking, they have all the features of Hilbert-style system.
Yes. Yes. All the features, and perhaps you have things like this, which you will call your form of cut, right? This is because you start on the empty set and you produce these alternatives. So it doesn't matter. It just comes from the table of negation. If I throw negation out, I still have a system for the negation-free part of classical logic. Actually, this is what's interesting about this. The characterization of the connectives is pure, just like nucleus. Questions? We go to this. Now this, I'm going to spend very few slides on this. This is going to be extremely important in the next talks, but I need to introduce it now so that you get used to it. And it's so associated to consequence the way I've been presenting it here that it's the right moment to talk about it. Okay, so what is this theory of oppositions? Most of you have heard about square oppositions, you know, that might be associated to logic somehow. And I claim that actually it is, in a very strong sense, intimately connected to consequence. I'm going to show you how. And I'm going to reformulate it in a modern version, which rather than having all terms contraries or contraries, you have antonymy duality. I'm going to explain what that means. And I'm going to also show that it does make sense, and it's really quite important to generalize this approach, not just to say connectives and their counterparts in the square, but also talking about logics themselves, talking about the rules that characterize the connectives. You can be just this tiny part and think about what it means to produce the dual or the contradictory or the antonymy. And there's a lot of confusion in the literature between antonymy and duality. So this is going to appear in the next slides in quite a few examples. Okay, it's going to be really important for the restoration connectives that I mentioned to you. Now we're talking more in the next lesson. Now, these are the things you know, propositional, classical, logic. I'm just organizing them as unary and binary connectives into squares. So the way I'm going to read this is that this symbol is going to be for antonymy, this symbol is going to be for duality, and this one for contradictoriness. Now, the contradictory connective to conjunction is, of course, the negation of conjunction, NET. And the dual connective to conjunction is going to be disjunction, as everybody would suspect. While the contradictory to that, which is the antonymy of conjunction, is NOR. Now, you could also start with your implication and think about what happens if you produce the contradictory of implication, the dual of implication, or the antonymy of implication. And maybe I should write it down here. Easier understanding and advertise of the notation. So I'm going to write with the formulas A implies B, and this is going to be the negation of it. So it's A conjunction not B. This is going to be B implies A, of course, or not A or B, A or not B, easier. And this is going to be the dual to this, which is, as you see, represented not A conjunction B. That's what I'm going to call the co-implication, and that will be useful in some moments. It's the dual to implication. Not so seriously taken by classical logicians, but it's quite an important connectivity. And if you forget how to read, remember that this is negation, right? So not A. Disjunction, conjunction. Okay. Now, it might happen that this square collapses and becomes just a line. It might happen, for instance, that the duality and contradictoriness coincide, as it happens with the by implication and the exclusive disjunction. Or it might happen that the contradictoriness coincides with the antonymy, and that a connective self-dual, like negation here and affirmation there, or identity, if you prefer. I like that name very much for connected. We call it affirmation as being the other guy, the antonymy of negation. Now, in modal logic, you also know this. You probably know this two here better than these two here. This box plus and diamond plus, the box and diamond from modal logic. I'm going to need much more these negative versions of it, the negative modalities here, but they're produced the same way as before. And you might have also a contingency operator and the non-contingency version, which are at once dual and contradictory. And in term logic and categorical, using categorical terms, and Aristotelian modern version, anachronistic version of Aristotelian logic, you all know the AEIO way of writing the squares. Now, this is fully symmetric for me, because I don't have just one direction, subalternation. I don't like that. It's very, should be pitching out. This is so putting you in a submissive position. Not gonna be subalternate, I'm gonna be dual. So you might put here your universal modifier, and it's gonna be the existential. They're dual to each other. It's not subaltern one to the other. And here you're gonna have the negative versions of it. So this is for all, this is for all not. This is exists, this exists not. And as you notice, whenever you go from this side to this side, you're putting negation, a sort of classical negation inside. It's an internal negation. Whenever you're going from here to here on the diagonals, you're putting an external negation. And the duals are produced by putting both an external and an internal negation, as everybody knows. Okay, questions?
I have one.
Yes.
It is a silly question, but you said that in the first line, the third diagram can be seen as a collection of.
This?
Yeah.
A collapse. I said it's a collapse because blue and red are the same.
Okay, but there can be a way that in this third diagram, the two connected collapses also?
No.
No? Why?
No, because this is the sort of classical negation of that, right? Nothing is a classical negation of itself.
Okay.
So that collapse will not occur. Okay. So you can flatten up a square in two different ways, but not this way you want to do it. Questions before I go into classical and non-classical negations? I will finish before lunch, don't worry, but I still have like ahead, and I'm willing to answer questions. I'm having lunch in the same place. Don't worry. We'll be there. Okay, so let me explain what is a classical, what is a non-classical negation. I was talking so abstractly about logic's consequence, now a theory of oppositions, only some examples included implication and so on, and this is supposed to be about negation, right? So let me explain what negation is, what it's not, or it cannot be. So what questions we make ourselves very naturally, what behavior do we expect from something to be called negation? Decent negation, as I put it sometimes in the past before I was actually censored by native English speakers telling me that I shouldn't use decent for this. I'm sorry. Legitimate negation. Is there any hope for agreement on non-negotiable properties of negation? And if opposition has anything to do with negation, what kind of oppositions could negation consist of? How could it be related to opposition? And also, what properties are shared, if any, by all negations? Okay, first of all, let me explain how I look at all connectors, not just negation. Not just me, Costa, other people have proposed that you look at them as punctuation marks. So what kind of punctuation marks? Well, conjunction might be thought as a way of cleverly internalizing at the object level the commas that appear on the left-hand side of the notion of consequence. Just you internalize it using this connective, this operator on sentences. And this junction internalizes the comma on the right. So far, so good. What about tops and bottoms? Well, they internalize the empty thing. So now we have a better thing to put in here. If you need something there. An implication is a way of paying a ticket to go from one side to the other. So you have this phi, it wants to go to the other side to join its friend psi, and the way you do it is by putting an implication there. Or you can push things to the other side, and remember this is like not psi conjunction phi, so you can use this co-implication inverting the order of the arguments, or you can use the other things I put in there. Okay, so this is NAND. NAND is joint denial. So if you have both things here, you want to put them together and push them to the other side, you use an AND. And that's the dual connective, pushing things to the left rather than to the right. And negation is a way of pushing things from one side to the other. And there is some redundancy here because actually classical negation is self-dual, so you have that you just need half of these things to produce the other half. But you need half of this and half of that to produce the other halves. So it's better we put all them together and we think of negation as being a way of pushing things from the left to the right and vice versa, or pushing things from right to the left and vice versa. Okay? So it's another kind of ticket that you pay and you don't even need an extra formula, or if you prefer, you can add these your tops and bottoms and produce a negation as phi implies bottom or as top co-implies phi. Okay, this is probably not how you have seen these connectors being presented, but I claim that everything we have seen is a consequence of this. All the rules from sequent calculi, tableaus, whatever you have seen before in your life can be inferred in the classical case from these abstract characterizations of connectors as punctuation marks. Okay, what about negation? Well, there's so many rules that people like, right? So I'm just going to flash them. You see them? Good. Okay, now, I give names to some of them because people like these names, like explosion, ex contradictione, in my version here, with all conjunction, implication, and so on. Consequência mirabilis, which was very much used in geometers in the Middle Age, particularly. Proof by cases, reduction ad absurdum. And you see that each one of these forms has a dual formulation, which are not so well known. They're the core cousins. And you have like double negation, elimination, introduction. You have things like contraposition, replacement, and so on. So various people have written various papers saying that these are the things I'm not wanting to negotiate about negation. Negation has to have contraposition. Negation has to have double negation, introduction. It has to. Because I say so. Okay, I won't say. Let me see what we could agree upon. Saying things that even I would agree with those people that would be proper propagation. First of all, first intuition I'm going to work on here. That oppositions are actually forms of consequence flipping, throwing things from one place to the other. And for instance, I'm going to say that two sentences are contradictory when they have these two properties here. The first one saying that, well, they cannot at once be asserted, and this one saying that they cannot at once be denied. So if one is asserted, the other one is denied, and vice versa. That's what contradiction is about, the classical contradiction, right? And that's what I'm going to use contradiction for. I'm not going to use the word contradiction to talk about the formula and its negation, unless it has these properties. Now, what if I don't want a contradictory forming operator? Then it has to fail one of these two things. Either it fails to be a contrary forming operator, so it will allow to a formula and its negation to be at once asserted. It will allow them to be both asserted. So you have some sort of gluts for negations. Or it will allow, by going against this, a formula and its negation to be at once denied. So there's a gap, negation gap in there. Okay, some people say that, okay, I agree that paraconsistent negation is not a contradictory forming operator, but it's a sub-contrary forming operator. No. It's a non-contrary forming operator. It might be a sub-contrary forming operator, but you need some luck, right? So it's a negative thing. It's not something. It's not a contra-reforming operator. Okay, you might say, okay, that's what makes it fail to be a negation, and say, okay, so intuitionistic negation also fails to be a negation for the same reason, because anything which is not a contradictory forming operator, which is not classical, is not classical. Like the identity plays a role, that the identity principle. It's not classical, then it's not classical, yes. So intuitionistic negation is not classical, in particular it's a negation gappy, and it's going to fail a lot of things from this slide, a lot. Okay, great, but people don't care about that. They care about the part consistent negation, which fails a lot of other things, which are just dual to those things. Okay. But let me explain to you, this is an intuition that I think I inherited from Jean-Yves Bezio, if he's in here. He was. He proposed that we should separate between negation and affirmation. Let me show you how that could go. So the idea is that hence thumbs down is bad, it's like false, right? You don't like it, deny it. And hence thumbs up is good, you assert it, you want it. And you see there's some problem here that a formula is asserted, and after you put this in front of it, it's still asserted. How can that be called a negation? And this also happens here and here. But here you have an option. You could also deny this guy. Oh, but you have a problem here because you have a formula that's denied, and after you put the connecting problem, it's still denied. So none of this stuff looks like it's flipping, it's inverting, it's changing anything. While these other things here look like they are changing, because you also always have a thumb up on one side and the possibility of having a thumbs down on the other side and vice versa. Well, let me just put these two things together to say what kind of rules that I defend that could be still associated to any kind of negation in the literature, and probably more things which you don't want to call negation, but at least this we could agree on. So you see the first one is saying that it's compatible to deny P while asserting not P. That's what I wrote here, right? It's compatible, this can happen. It's saying that it can happen that you deny P, thumbs down, while you assert not P. So something is being inverted. Something that was false becomes true. Maybe it may also be false in some other situations, but at some situations, at least here, it might change, might flip the value. And here's the opposite, it's saying that it is compatible to assert P, thumbs up, while denying not P, thumbs down. Now, I have been defending and proposing this quite popular nowadays, that these are principles that everybody is willing to accept. Negative principles, principles about compatibility, not about consequence. And there's a more general version of them saying that doesn't matter what's the number of negations that you put, if you add an extra one, you should still be able to flip some stuff. Something that's true should become false. Something that's false should become true. If everything that's true becomes false and everything that's false becomes true, then you have classical logic. But some, okay? All right, so I'm going to call a legitimate negation one that respects all those rules, which seem to attract some sympathy from both classical and non-classical logicians. Anyone who wants usually to call something a negation, or most people, let's say, there's always someone who's going to call something else a negation. But hard to find counterexamples of that. Here are a lot of definitions. First slide with really important definitions, and it's the last, this part. So let me try to read them. We have already needed some of these things before. So when I write, there's the invisible empty set here on the right. So this is saying that one may assert all the sentences of the language at once. Okay, why would anyone? Some logics do that. Some logics allow for the basic reading, in particular by making absolutely everything true. The logics from inconsistency that I will present in the next sessions do not allow for that. They have no dadaistic readings. There are no models which are models of all the sentences at once. And this is the dual principle saying that you may deny everything at once. So by denying everything, I say you take a nihilistic approach. And by asserting everything, you're being dadaistic. Everything is good. Okay, and whenever you have these two things here, saying that you cannot assert these two formulas at once, and you cannot deny them at once, I'm going to say that the negation is definite. So some people call it a classic light negation. These two things come directly from the internalization that I proposed in the first slide in this series, pushing things from one side to the other. You start with P in both sides, and then you push the P here, it becomes an off P. Right? That's pushing things to the other side, one step. You start with P and P, which is reflexivity, and you push the P on the left to here, and here it is, and vice versa. Okay, and what it means to be paraconsistent, a negation is going to be called paraconsistent when it has this behavior of making it compatible to assert a formula, some formula, with its negation, while denying some other formula. And what does it mean to be paracomplete? When you may deny a formula in its negation while asserting some other formula. Now I'll read this again when I put some assertions and denials back here. The next click. And I'm going to call paranormal negation, which is either paraconsistent or paracomplete, and paradefinite if it's at once. Paradefinite and paracomplete. There will be examples of this, a lot of them later on. Just to rewrite so that you can have a reading without so much formality. Admit that the basic reading just means, as I said, at once you may assert all the sentences. Nihilistic, at once you may, there's a denied, of course. Copy and paste. And a sentence is asserted if and only if it's denied. It's what's characteristic of classic like negation. And this is important. A paraconsistent negation is not made simply by introducing models for a formula and its negation. It's made by introducing non-dadaistic models for them. So models in which you have a formula and its negation at once being asserted while not asserting everything else. Adding a dadaistic reading to a logic doesn't make it paraconsistent. You need more. And to be paracomplete, as I said, you need a non-nihilistic reading. So not everything is denied while these two things are. So if you want to read from right to left, the denial of these two things does not imply the denial of that. People don't like to read this denial-based consonants, but we'll look here at some points here. Okay, questions? Yes?
I think it's just about clarification about the dadaistic reading application. Say that there were logics reading dadaistic. I guess you mean that we can construct from a system. I don't think somebody has defended those.
I'm going to show some examples of logics which are out there which allow for dadaistic readings. For instance, LP. It has models for all the formulas. I'm going to show some examples. Thanks for the question. Yes, that's a very good question. Intuitionistic logic.
For questions, we would like that the
I will repeat the question.
come here because we are.
I'll repeat the question so that he doesn't have to come. So the question, thank you. The question was whether there's some relation between paracomplete logics and intuitionistic logic. Intuitionistic logic is an example of a paracomplete logic. Other questions? No, this must be really bad. I've been saying outrageous stuff here and you don't have questions. Objections. So I'll continue. There's no objection. It's almost over. This is actually the last set of slides because the final one is a couple of warnings which I'm just going to display and answer if you ask me. But this one is really important for introducing what we want to do. I promised to talk about restoration connectors. So let's say what they are about. They are about to go inside a non-classical environment and try to recapture classical behavior, recover what has been lost. What do I mean by this? I mean, in a very informal sense, say that this can be formalized and will but at the moment saying that para consistent logics fail something, some assumption which the classical logician likes, which is the assumption that everything behaves consistently. We call it the consistency assumption. And while the dual para complete logics fail, what I call the determinateness assumption, please help me pronounce this better, which is the dual. As you have seen before, and you're going to see again. Now, so I failed these assumptions from classical logic, and you might say, that's really too bad because I loved it. I loved classical logic. Can you recover it for me? Can you bring it back? Okay, let me show you some ways you can, and why is it so bad that you lose these assumptions. Let me focus on the para consistent examples, examples from para consistent logic. For instance, an extremely important principle in classical logic, and actually in life out there, is so-called disjunctive syllogism. I usually say that it's the one that prevents you from dying, and you have to do it really fast. You're driving on the road. There are two ways, but that way the road is blocked. You should be quick. Go to the other one, right? This has to be practiced quickly. So go to the other one. And resolution, theorem provers, prologue, lots of things are based on this. So the world is going to ruin if you don't have it. But in classical, in para consistent logic, you don't have it. Basically, you don't have it in general because, imagine, you might have a situation in which this disjunction is true because P is true. And Q might be false. Now, if you have not P and also P, you would very easily, using your favorite disjunction, which is the standard one, something like this. Disjunctive syllogism here. Give you Q. This means that colors. You only need this and this on Q. So your logic is not para consistent. So being para consistent prevents you from doing that as long as you allow this single step to happen here, which is people who like to allow for most understanding of this junction. Okay, and another one is contraposition. Very simple also. If you have this, which even an intuitionistic logician would allow, and if you have this rule, which is in there, allowing you to conclude Q, again, by a single step, which people would probably allow you to take, you would conclude anything from contradiction. So para consistent logics are going to throw some stuff away. For one, Karl Popper looked at this and said, oh, this is really bad, so you cannot do para consistent logic. Right? So he was almost a forerunner of para consistent logic, except for his prejudice, which is very common. But actually, he couldn't develop one, but he tried. So in a sense, he had some right ideas over there. Now, you might say, that's too bad. The second one is not so bad because intuitionistic logicians also lose this one. But you have other versions of contraposition which are respected in intuitionistic logic, which are not respected by a bold para consistent logic, one which does not allow for partial exclusions. I'm not going to enter into this, just showing you things which are actually people would like to recover. So how could I recover? One way of recovering is by doing the course next week on translations between logics, finding a way of defining another negation which is classic-like, and translating your inferences and saying, well, indeed, it fails for the original negation, which is the para consistent negation, but there is another one for which you can recover disjunctive syllogism and contraposition, as long as it behaves, this new negation behaves well. The second idea, which is the one that I'm going to explore in this course, is, okay, why was it when I explained that things might go bad? Because you might have a way of asserting these two guys, and you don't want to assert everything from there. You might have a model for P and not P in logics which are strange enough. Now, what if I were to eliminate these models? What if I were to say something about P and say, well, if I know this extra stuff about P, then I can still conclude anything. And what is it that I need to know? Well, I lost the consistency assumption, remember? What if I were to say that P behaves consistently in a certain sense? And that's where the logical formal inconsistency are going to be born. By adding extra assumptions and internalizing, just like any connective internalizes meta-theoretical stuff into the object level language, you might be able to recover adjusted versions of disjunctive syllogism and contraposition. Okay, you're going to see this many times again, so don't worry. But you see that the main idea here was adding a circle with a smile. And for you to remember, a smile is a paraconsistent negation, of course. While frown, if something would happen like the Netherlands, or complete negation, intuitionistic like, quite sad, bad weather. Okay. Now you remember smiles and frowns. Questions? So all this is going to be developed in the next talk. Advertise. Don't disappear from today to tomorrow. Please, question.
Please, could you come in front of?
I can't hear. I can repeat the question.
You repeat.
I repeat the question. Yes.
Not familiar with these topics.
Yes.
Idea one, it is a translated version. If your or those translations are correct, maybe the consequence is not the same. In that case, we may think that those are same versions of this.
The very last part I didn't hear. Could I think?
Because when we translate the distinctive syllogism with another negation and have the same consequences, and we may think that they are the same distinctive syllogism, so that don't we have any problem with
Yes, thank you. So this is about the first idea here, that you translate the negation you have into another one, which gives you back disjunctive syllogism or contraposition.
Repeat the question.
That's the question. That's the question. I'm not answering yet. That's the question, right? That was the question. So, what is there a problem there?
Yeah, if the consequences are the same.
Yes. So that's the idea. If the translation is faithful, then the consequences should be the same.
So, isn't it mean, doesn't it mean they are probably accepted the principle explosion?
Does it mean that it accepts the principle of explosion? It accepts the principle of explosion for the square negation. By definition of what it means to be classic-like. The square negation is classic-like, so it does have, by definition of being classic-like. This. While the other one, if that logic turns out to be paraconsistent or paracomplete, might fail to have that property. It's paraconsistent. It's paracomplete. It might fail to have it. Well, let me make it even better. As I said, here is a smile. Here's a frown. So if you translate smiles into square negations, and this is a conservative translation, a good one, faithful, then you're going to be able to recover what had been lost because it was a black triangle, it becomes a white triangle. You might not want to recover, but if you do want to recover, that's a way of doing it. And some logics do it even without you wanting. They just allow you to do it. Okay? So it might be a discovery that your favorite logic does it. Yes, Kerian.
Please.
I can hear. I can listen quite well.
Yes, but
I will repeat. I've been repeating all the questions.
everybody would like.
May I repeat this question?
If you could come here,
Okay, it's taking time.
it would be
You
better.
might be late for lunch. Can you say?
Please.
Oh, yeah.
Just I can listen.
You can see it. Your second idea, you introduced the smile operator.
Yes, my second idea introduced the circle
The circle.
with a smile inside.
Smile operator.
Yeah, I'm gonna use the smile next one.
This example
Plan to
is
smile.
about the notion of raw behavior.
Yes.
Of the calculus, the calculus.
Yes,
Is
yes.
correct.
So the question is whether the circle with a smile inside resembles, for a good reason, the notion of good behavior from Newton and Costa's approach to power consistent logic. Yes, exactly. That's just right. Great. Other questions? Yes.
Yeah, so you mentioned bold power consistent logic.
Yes.
Doesn't allow for partial explosions. What do you mean by that?
Very good question. So if you think that explosion has to do with deriving anything, and now on purpose I put something here, I might want also to avoid deriving some formula which has nothing to do with P over there. An example that was mentioned by Evandro in his talk, minimal intuitionistic logic allows you to do weird stuff like this. Now, one might complain that a logic that does not derive anything, but still derives the negation of anything, is still pretty bad. So being boldly power consistent means to avoid deriving a particular set of formulas which is not, well, not theorems of your logic, but they become just like after you put some pair of formulas there, one of which is the negation of the other. So you start to, instead of explode and trivialize a logic and derive all the formulas you derive, for instance, all the formulas with a particular shape, with a funny shape, all the implications,
Yes,
all the
that's a bold power consistency.
both power consistent logic would avoid both problems, would avoid deriving arbitrary formulas, but also would avoid deriving arbitrary classes of non-theorematic formulas.
Right. Whereas a non-bold power consistency is one that prevents you from deriving
Yeah.
this certain part. Yeah.
Minimal intuitionistic logic is power consistent in this sense, but still allows you to derive any negation. So it's pretty bad with power consistent logic. Those for a partial explosion. Yes.
About the logic of formal consistency, actually, they introduced the circle operator that talks about consistency. But some of them, or all of them perhaps, they also allow you to define a classic negation. Does that mean that idea number one is some kind of byproduct or side effect of idea number two?
That's a very good question. So the question was whether if the logics of inconsistency allow you to introduce these circles, and with the help of that circle, you can define a classic-like negation. So idea number one would be a consequence of idea number two. Whenever you implement idea number two, you would also solve things through idea number one. Is that right? Okay, so the big surprise, I'm going to present some logics which have a circle operator but have no definable classical negation. So it's again a big mistake in the literature to assume that you can always define a classic-like negation. You cannot always define. But you might have the circle without having any definable classical negation. Questions? Yes.
Yeah, so when you are explaining that you are not introducing formulas of some non-mentioned Q, so there might be some connection between paraconsistent and relevant logic.
Yes. Yes. This is a sort of relevance, right? They don't guarantee all the other ones. They don't guarantee variable sharing property in general. They don't guarantee everything that a relevant logic would guarantee, but any relevant logic, or relevance logic, must be at least paraconsistent and paracomplete. So these are particular cases of relevant logics. Okay, so the final slide is basically just a number of warnings and questions. I'm gonna just display them there. The time is almost over. I can read them, I can answer any one of them. My answer to most of these questions is no. So it's up to you to decide which one you want to talk a little bit more about. Yeah. Yes?
The first, please.
Okay, let's start with the first. So, our power consistent logic is designed to deal with true contradictions. First of all, as I said, they're not even designed to deal with contradictions at all, right? True ones, I don't even know what that is. So, I think this is a very interesting project, but it goes quite orthogonal to ours. If you have a logic with true contradictions, you want it to be power consistent, but you don't need a power consistent logic to deal with anything called true contradictions.
Oh, Grande. Yes.
Yes, it's going to be here in a moment.
So you would say that our consistent logics can be very much useful for ontology, true contradictions, or
Yes. Certainly. If I would say if they're important or useful for an ontology with true contradictions, yes, because they're essential. If you want true contradictions, if you want dialectias, you need the logic to be power consistent. You don't have the odd direction. So power consistent logic doesn't need to be about that.
Okay.
Yeah, something more than one vision.
Of course, you wrote your PhD on this, right? Of course it may, it should. It must. One is a smile. The other one is a frown. Oh, you can have many. You can have many smiles, many frowns, let them bloom.
What's the negation of consistency?
Oh, that's a very good question. Does the negation of consistency represent inconsistency? Depends on which negation. Right? Because now we have many, right? We have just accepted that there could be many. So, if this represents consistency, what's the negation you're talking about? Is it the classical negation of it, or is it the power consistent negation of it? In the next session, I'm going to define inconsistency as something that's going to turn out to be the classical opposite of consistency. Sometimes they're equivalent, but not always. Depends on the logic. Yes?
I think that the last two questions are
Not really, because the first one is a yes. The second one is a no. So, as I'm going to show in the next talk, the dual to consistency is undeterminedness. Determinedness is the antonym of consistency. There will some beautiful squares also coming there. Just wait and see. Because I cannot do a black square with a smile or a frown, I'm going to do it like this. It is somewhere here. You're gonna have. You're gonna have. Put it in here. Demons, right? It's consistency. And here you have inconsistency. The antonym of this is going to be determinedness. The logic is called indeterminateness. And the opposite of it, the contradictory of it, is going to be the dual to consistency. It's undeterminateness.
That's all either, right? And we're not talking about methods. You're right.
They're going to be all internalized in the next talk. They're going to be all internalized in the language. These four unary connectives are going to be internalized in the language. Yes? Also, right? You also.
Not only with negation, but also with negation. So my question is, what's the difference of the C1 of negation and smile and all negation, just with the symbols? Because it seems that it gets everything to work.
Yeah. It's a very, let me see if I understand. The question is the difference between all these symbols of negation that I have introduced, like this square negation.
What are they called negation?
When I talk about a negation, in general, I'm going to use a curly symbol. But when I tell that it's a classic-like negation, I would immediately start to write it as a square symbol. So you have to ask me in every slide. And sometimes instead of using the curly, I'm going to use a smile in the front. It's not that they are all always different. It's that I'm going to choose symbols for each slide which are useful to make us help reminding what we're talking about. So whenever I write a smile rather than a curly negation, you're going to say, oh, he intends to talk about a power consistent negation, right? It's just to help. All that there is to negation for in this course is going to be this. Negation should invert things. Some true things should become false, some false things should become true. That's all.
They should or they might?
They might. I said should.
Yeah.
They should or they might.
I was dressing the shirt of the classical logician. Must. No, actually, shouldn't.
No, you said that some things.
Some things, right? I said some.
Okay,
So some true things become false when you put a negation in front of them.
It's necessary to be possible.
This might happen. Some funny logics will do that. Actually, you don't need to like them. They exist. They're out there. Yes.
The fourth question, please, about the principle of non-contradiction and consistency.
Yes. Oh, yes. No relation.
Yes.
No relation.
No relation.
No. The principle of non-contradiction, the way I put it here, has to do with something that happens at the consequence level. Now, maybe when you internalize that thing, it might happen to coincide with an object language formula, which is that one, but that's a fetish formula.
Of course.
Right? You might like it or not. It has absolutely no reason that you read that conjunction and those two curly negations the way I want you to read. You tell me the rules and then we see that if it works or not.
Object level.
It depends on the logic. So depending on the logic, that curly negation, if it's classical negation, perhaps it's just equivalent to what I formulated before. But if it's non-classical, then it's not. And one thing that I want to make it very clear is that even if you agree that P conjunction, not P, with this negation being the para-consistent negation is the thing you want to avoid, the way of avoiding it is by putting a classical negation in front of it, not a para-consistent negation in front of it. That's the way of saying that it's false, because that's the role of classical negation. And some people have mixed stuff over there and talk about this as if the two formulas were equivalent. They're not always equivalent. They might be, depending on the logic.
Right, thanks.